Good morning. Today, I'd like to talk about a method called extrapolation to the limit, by which we can take several approximations to something, combine them, and even though the individual approximations were not very good, the result at the end will be excellent. I'm going to think of having one of our differential equation problems. I know the solution, or at least an estimate of it, at t equals tn, t being short for theta, and I want to know an estimate of the approximation at theta equals t out. Using Euler's method, we could do such a thing. I'm going to make up a two-dimensional table with indexes that start at 0 and go up to some ending value, which I can adjust as I like. I'm going to calculate the estimate of the solution at t out using one step of Euler and call table entry 0, 0 the result. After that, I'll go back to the original problem. I'm going to move from t in to t out as before, except this time I'm going to do it in two equally sized steps. That is, I've doubled the number of intervals involved. So I'll start with my estimate of the solution here. I'll increase the theta by half of the width of the interval. I'll use Euler to get an estimate of the solution there, and then using that, I'll move forward one half of the width of the original interval again. I could restart the problem again, except this time I'm going to use four equally sized steps. I'll call the result table 2, 0. Then I could use 8 steps. I'll call the resulting estimate table 3, 0. If I wanted to, I could do 16, 32, 64, and so on until I decided that I'd done enough of this. For purposes of illustration, I'll let the largest index, either row index or column index, be 3, although similar ideas will let you do as many rows and columns as you care to. I get this column of numbers by doing various Euler-type approximations, and I'm going to get these other numbers by using a certain recursion formula. Table number I, k is going to be the number in the table immediately to the left of entry ik plus a fraction. The top of the fraction is table I, k minus 1 minus table I minus 1, k minus 1. The bottom of the fraction is 1 less than 2 raised to the k power. I have a playlist in my YouTube account called Extrapolation, which describes this procedure in gory detail and proves that what I'm about to say is actually valid. If rounding errors are not a significant problem, then this number is some approximation to the thing I'm trying to calculate. This number will be a much better approximation. This will be better still. And this will be better still. It's worth mentioning that for every additional row and column in this table that I'm going to construct, I have to do roughly twice as much work as the preceding row and column because the number of subdivisions has been doubled. For practical reasons, we can't make the number of rows and columns enormous, but in the absence of rounding errors, if we could make this number as close to the thing we're trying to calculate as we care to. I want to try this idea out. We're going to use that same test problem again. Second derivative of u plus u is 1/9. U at theta equals 0 is 1, 6. U prime at 0 is 0. Theta going around 0 to 2 pi would be one orbit. So by putting it this way, I emphasize the fact I'm going to do 10 orbits here. This is the problem that we already know the solution to. Putting in 1 and -1 for cosine theta gives me the maximal and minimal values for u. U is at least 1 over 18 and no more than 1 over 6. So I'm going to refer that to be u is somewhere in the vicinity of 1. I'm not going to be very precise about that language. When I write my program, I have a choice to make about how much numerical precision that I've got. The compiler that I'm using gives me an option to do single precision, which is 32-bit arithmetic, double, which is 64, and quad. If you gave me some number and I stuck it into the computer, the number that's in the computer typically will not be the exact number you handed me because of the finite number of digits that I can store. In double precision, I should be able to get about 15 digits of accuracy in a perfect world. In quad precision, 30, 31, 32 digits of accuracy at best. If I have a method that does that, gives me 15 or 16 digits of accuracy in double precision, and in the range of 30 digits in quad, then I've got to regard that as being excellent. That's as good as you can do. In my program, I'm going to use 1,000 steps for the Euler method, and I'm going to do 10 orbits. Within the extrapolation routine, I'm going to allow the indexes in my extrapolation table to go from 0 to 12. I've run the program, and I want to look at the error file. I'm doing this in double precision, so in a perfect world, if everything is working correctly, the errors should be on the order of 10 to the minus 15 or thereabouts. At the very beginning, of course, the error is 0 because that's where we know the value of the solution. After that, I get numbers that look like 10 to the minus 17. I see some 10 to the minus 16s, 10 to the minus 15s. I'm just going to page quickly through this, making sure I don't see anything bad. I saw some 10 to the minus 14s. That's not so bad, and I never see anything worse than that. I'd have to say this is working pretty well. Now I'm going to do the same thing, but in quad precision. Now I'm going to do the same thing, except in quad precision. I will, again, use 1,000 subintervals, and I want to do 10 orbits. Let's look at the errors again. Since I'm in quad precision, I should be getting on the order of 32, 31 digits of accuracy, something in that general neighborhood. 10 to the negative 33, 10 to the negative 34. Everything looks good at the beginning. Just like before, I'm going to page through this and see if I see anything particularly troubling. I'm seeing some 10 to the minus 31s, but 31 digits of accuracy is still pretty good. I never see anything bad. This tells me that this extrapolated Euler method, at least for this kind of problem, seems to be working quite well. In the next video, we're going to finally get back on track and think about the orbit of the planet Mercury. Until then, I hope everybody has a good day, and I'll talk to you again soon.